Hi, welcome back. In problem 6, you're given a piece of C code and you need to use it to determine the specifications of a cache. First, let's understand the access pattern of this C code. Let's say we have an array. And in our C code, we have a nested for loop. In the first outer loop, the inner loop will start at index 0 and increment its index by stride. And then it keeps increment the index by stride until it reaches the end of the array, or it cannot further increment the index. Sorry. So this is exactly the number of stride, and yeah. So after it reaches the end of the array, it will move on to the second iteration, or second outer iteration, and the inner iteration will start at index 1, and also increment by stride every time until reaching the end of the array, and then move on to the next outer iteration and start at index 2, and also increment the index by stride every time until reaching the end of the array. Okay, so in total there should be a stride number of outer loops, and in every inner loop it looks like this pattern. In question A, we have a 32-byte fully associative cache with 8-byte blocks. So from this information, we know that our array should have 64 entries. And there should be 32 bytes divided by 8 bytes equals 4 different blocks. Okay, so first, when stride equals to 1, there should be only one outer iteration, and in this only outer loop, the inner loop will start at index 0 and increment its index by 1 every time. So it's essentially equivalent to accessing the array in sequence. So the access pattern should be 0, 1, 2, 3, 4, 5, 6, 7, 8, blah, 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 until 63. And if we look at this sequential pattern, we will notice that every 8 contiguous accesses are within the same cache block. And on the first cache access to every such block, we will have a cache miss because we have to fetch this whole block from memory into the cache. It's a compulsory miss. However, for the next 7 accesses, since the block has already been fetched into the cache, we will have 7 cache hits. And this should be true for all other blocks. Therefore, the miss rate for stride equals to 1 should be 1/8. Okay, and then when stride equals to 2. Now we have 2 outer loops. And in the first outer loop, the inner loop will start at index 0 and increment its index by 2 every time. So its access pattern should be 0, 2, 4, 6, 8, blah, 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 until 62. And in the next outer loop, it will start at index 1 and increment its index by 2 every time. So its access pattern should be 1, 3, 5, 7, 9, blah, blah, blah. Okay, so as we can see, in every inner loop, every 4 contiguous accesses are inside one block. And since there are 64 different entries, and in every inner loop, it should access exactly 8 blocks, which exceeds the total size of the cache, which only holds 4 blocks. And that also means after we iterate through all the entry in the first outer loop and goes back to the first block inside the second loop, although this 1357 block is in the same block as 0246, because we have accessed 8 different blocks in the first iteration, this block has already been evicted from the cache. Therefore, after we come back to the 1357 in the second iteration, we will still have a cache miss on the first access. So in the first iteration, for every block, we will have a cache miss on the first access to one block, and followed by 3 cache hits. And the same thing will happen also in the second iteration. That is, in every block, we have a first cache miss comes with 3 cache hits. Therefore, when stride equals to 2, the miss rate should be 1/4. And after that, let's look at stride equals to 4. It's also very similar to stride equals to 2. We just have 4 different outer iterations this time. And in the first outer iteration, it will access 0, 4, 8, 12, blah, 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 etc. And in the second iteration, it accesses 1, 5, 9, 13. And in the third one, it accesses 2, 6, 10, 14. And finally, it accesses 3, 7, 11, 15, blah, blah, blah. So in every inner iteration, it still accesses 8 blocks each time. And also, you can notice that every 2 contiguous accesses are within the same block. Therefore, on a first access to this block, we will have a cache miss, and next we will have a cache hit. And for the similar reason as stride equals to 2, after every inner iteration we goes back to the first block of this array, although it's in the same array as the previous 04 block. Since we have already accessed 8 different blocks into the cache, we have already evicted this block. We have evicted the block for 04 from the cache. Therefore, when we access 15, we will still have a miss on the first access and a cache hit for the second one. And for the similar reason, for this 913 block, we will also have a miss for 9 and a hit for 13. And similarly, for 26 block, we will have a miss for 2 and a hit for 6. And for this 37 block, we will have a miss for 3 and a hit for 7. Therefore, when stride equals to 4, our miss rate would be 1/2. And for stride equals to 8, the reason would be very similar. And for every because every contiguous access would be in different blocks, so we will have exactly 1 miss for every access, and the miss rate would be 1/1 or just 1. Okay, and then things get a little bit different when stride becomes 16. When stride equals to 16, we will have 16 different outer loops, but in every inner loop, we will access first 0, 16, 32, 48. And in the second inner loop, we will access 1, 17, 33, and 49. And blah, blah, blah. Let's say we will access until 7. And this one should be 23 and 39 and 55. And then we'll keep going from 8, 24, 40, and 56, and keep going until we reaches 15, 31, 47, and 63. So probably you have noticed that in every inner iteration, previously we will access 8 different blocks in every inner loop. But this time, in every inner loop, we only access 4 blocks, which exactly or fit in our 4-block cache. Therefore, in the next iteration, when we come back to this 1, the block for 0 has not been evicted yet. It's still in the cache. Therefore, we will have a cache miss for access 1. We will have a cache hit for access 1. And similarly for 16, we will have a cache miss, but in the second iteration, when we come back to 17, the block for 16 and 17 has not been evicted yet. So we will also have a cache hit. And similarly for 32 and 33, and 48 and 49. Actually, this will keep to be true until we have until this inner loop starts at 7. We will still have a cache hit for all of them because those blocks has not been evicted yet. However, next when we reaches the inner loop that starts at index 8, we'll notice that this 8 is different from the previous block that ranges from 0 to 7. Therefore, this time we will have to have a miss. And also similarly for 24, 40, and 56. And after this iteration, we will have exactly 4 blocks that is holding the blocks for 8, 24, 40, and 56 inside the cache, instead of the previous 4 different blocks. So once again, we will, after we go back to the next iteration when we have a 9, 25, 41, and 57, the cache blocks are still inside the cache. So we will have cache hits. And we will keep having cache hits until the last outer iteration when we start at 15, and then 31, 47, and 63. These would still be for cache hits because the corresponding cache blocks are still inside the cache. Therefore, as you can see, if we look into the access in this manner, for every cache block, we still have only 1 cache miss in the first access, but have 7 cache hits for the next 7 accesses, even if they are not accessed in a sequential way as the access pattern when stride equals to 1. But we will still have a miss rate of 1/8. Okay, finally for stride equals to 32. It also have a very similar pattern as the stride equals to 16 situation. In the first inner loop, we start at 0, and then we have 32, and then we go to the second outer iteration, and we start at 1, and then 33. We will keep doing this until the inner loop starts at 7, and with another 39. Okay, and then we will have an inner loop starting at 8, and also coming with 40, and a 9 with 41, and it's keep going until the inner loop starting at 15, and with a 47. And after that, we will have an access to 16. And come with a access to 48, and then is 17 with access to 49. And blah 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 until we have access that is starting at 23, come with an access to 50 should be 55. And finally, we will have a last group that is starting at 24, come with an access to 56, and then 25, 57, blah blah blah, until 31 and 60. 63. Okay. So similarly as the case when stride equals to 16, in every inner iteration or every inner loop, we only access 2 blocks, which fits inside the 4-block fully associative cache. So that when we come back to, so first we have a cache miss to 0 and 32. But when we come back to 1 and 33, the block for them are still inside the cache, so they will have a cache hit. And we will keep, okay, I'll do this in this way. So until this inner loop was starting at 7, come with a 39, we will still have a cache hit, because those accesses are within the same block, and they have not been evicted from the cache yet. Okay, and next we access 8, which should be a cache miss because it's not one of the previous 2 cache blocks. And so the same for 40. But also, once again, for the next 7 groups of accesses, we all have cache hits because they are in the same cache block and they are not evicted by the cache. And also similarly for the next group, 16 and 48, we will have a first cache miss to them and then followed by 7 cache hits. Finally, we will have a cache miss for 24 and 56, and commed with 7 other cache hits within the same cache block. So as you can see, we still have exactly 1 miss in every cache block, commed with 7 other cache hits. So the miss rate for stride equals 32 is still 1/8. Part B is much trickier because this time we need to reverse engineer the specifications of the cache. Although we don't know anything about the block size or any other cache structure, we can still deduce something from the stride equals to 1 situation. Because from previous part, we know that when stride equals to 1, it will just be a sequential access to every add item or entry inside the array. And for a sequential access, the miss rate actually doesn't matter how the cache looks like, because we never jump over different cache blocks. We are always accessing the blocks in sequence. Therefore, since the question tells us the miss rate is 0.25 or 1/4, that means in every block we will have a first cache miss combed with 3 cache hits. And next, we will have another cache miss with 3 cache hits, which tells us that our cache block should have 4 bytes. So we know that our block size must be 4 byte, therefore there should be 64 byte divided by 4 byte equals to 16 different blocks inside the cache. But we still don't know what the structure it is. Is it a fully associative cache or a set associative cache? We don't know. Since we don't know anything about the cache, so why not just assume first that it is a fully associative cache? And try to simulate our different strides using a fully associative cache to see if the miss rate is consistent with our simulation. So first, when stride equals to 2, similar to our part A, we'll access 0, 2, 4, 6, 8, 10, blah, 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 until 126 in the first inner loop. And in the second inner loop, we will have 1, 3, 5, 7, 9, 11, blah, 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 until 127. And if we do some mathematics, we will notice that in every inner loop, we will access 32 blocks. Because every 2 contiguous accesses are within 1 block, and we will have 32 blocks in every inner loop. And this means that after we come back to the 1 and 3 in the second inner loop, this block has already been evicted by the cache, because the cache can only hold 16 blocks. Therefore, when we access 1 and 3, we will still have a cache miss on 1 and a cache hit on 3. Similarly, for 5 and 7, a miss for 5 and hit for 7. And yeah, not to mention, in the first iteration, we should have a miss and a hit in every block. Therefore, from this assumption that it's a fully associative cache, we will have a miss rate of 1/2, which is consistent with the question. So our assumption is still okay at this point. Next, let's take a look at stride equals to 4. Stride equals to 4. And we will have 4 inner loops. In the first inner loop, we will start at 0, and then 4, 8, 12, blah, 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 until 124. And then in the second inner loop, we will start at 1, and then 5, 9, 13, until 125. Next, in the next loop, we will start at 2, and then 6, 10, 14, until 126. And finally, we start at 3, and then we have 7, 11, 15, until 127. So, as you can see, in every inner loop, every access is in a single block, and every adjacent block access pairs are in different blocks. And in every inner loop, we will still have access to 32 blocks. which cannot be held by the hash. So in the first iteration, every block, every access should have a cache miss because there are compulsory misses. And then when we come back to 1 in the second iteration, since the cache cannot hold 32 blocks inside the cache, so this 0 block has already been evicted, and this 1 should give us a cache miss. And similarly for 5 and 9, we will all have cache misses. And then in the next iteration, when we come back to 2, once again, we have evicted the block for 1. So this 2 will also give us a cache miss. So after we have checked all these accesses, we should notice that we will have cache misses for all of the array accesses. Therefore, our miss rate should be exactly 1, which is also consistent with our question, so our assumption of fully associative cache is still okay at this point. Next, things become tricky when stride equals to 8. When stride equals to 8, we will have 8 different loops, and in the first loop, we will access to 0, 8, 16, blah, 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 until 120. And then in the next iteration, we will have, we'll start at 1, and then 9, 17, blah, 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 until 121. And then in the next iteration, start at 2, and then 10, 18, blah, 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 until 122, and etc. So this time, we still notice that every access is just like every adjacent access pairs are still in the same different blocks. However, this time, because we are kind of jump over a cache block, notice that there's a cache block from 4 to 7 in between. We'll kind of jump over one block. Therefore, in every inner loop, we will actually only access 16 blocks. And if our cache is a fully associative cache, it can fit in our cache just well. And if we come back to 1 in the next iteration, this block should have not been evicted yet, and we will have a cache hit. And if this is the case, we should have a miss rate of 1/4 if we use the similar process we made in part A. However, the question tells us that when stride equals to 8, our miss rate is still 1, which is not consistent with our assumption. That means our fully associative cache is not true. So what happens is that there should be more than one set inside the cache, so that in every inner loop, these cache blocks cannot be held by just one set, and all the old blocks will be evicted by the cache, so that after we come back to the first block in the next iteration, we will not find the block inside the cache and we'll have a cache miss. So since fully associative cache is not true, let's assume it's a 8-way set associative cache. I make this assumption because we have 16 blocks in the cache. If it's an 8-way set associative cache, then we will have 2 sets. Okay, if we have two different sets in the cache, then in every iteration, our 16 blocks will actually go to the same set inside the cache if we do some address decoding. And this will be consistent with our question because these 16 blocks cannot be held within the 8-way set, and we have to evict some old blocks in one inner loop. And that's why when we come back to the first block in the next iteration, that block has already been evicted, and we will have a cache miss. Yeah, another illustration is you can draw a cache here. And if we divide it into two sets, so first 0, 8, 16, 24, and then 32. Sorry, I should make this larger, but 32, 40, 48, and 56 are all inside the first set. And similarly, 64, 72, 80, 88, blah, 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 until 120 should also be inside set 0. Therefore, when we fetch in the block for 64, we have to evict the block for 0. And when we fetch in block 72, we have to evict the block for 8. And when we come back to 1 in the next iteration, we will find that the block for 0 has already been evicted. Okay, so currently 8-way set associative cache meets our assumption, is our assumption, and it is consistent with the question. So let's just keep using this assumption for stride equals to 16. And when stride equals to 16, we will access 0, 16, 32, 48, blah, 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 until 1. Oh wait, it should be 112. Yeah, 112. And in the next iteration, we will start at 1 and then goes to 17 and then 33 and then 49, blah, 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 until 113. Okay, so as you can see, once again, every adjacent access pairs are in different cache blocks, but this time we are kind of jump over 3 different blocks. We are jumping over the block for 4, 8, and 12. Sorry, jump over the blocks for 4, 8, and 12. And that means in every inner iteration, we will have access to only 8 blocks. And if we are using our previous assumption of the 8-way set associative cache, these 8 blocks should exactly fit inside the one set of the cache, so that after every iteration and coming back to the first block, we should have a cache hit. And similarly for 17 and 33, etc. And if that is the case, our miss rate should be 1/4 if we use the similar process we used for part A. However, the question still tells us that the miss rate when stride equals to 16 is 1. So that means our 8-way set associative cache assumption is not correct. So what we can do is we further divide the cache into 4 sets, or a 4-way set associative cache, so that every set only has 4 blocks. And if we do some address decoding, we will see that 0, 16, 32, 48, blah, 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 until 112, these blocks all go to the set 0 of this cache. Therefore, because we access 8 different blocks, our one set cannot hold that many of blocks and have to evict the old block for 0, 16, and 32. And after we come back to the first block and access 1, we will notice that the block for 0 has already been evicted, and we will have a cache miss for all of them. And in this situation, we will have a miss rate of 1, which is consistent with what the question tells us. Okay, and Next, we can use our assumption of a four-way set associative cache to test the case when stride equals to 32. And actually, similarly to the previous two situations, when stride equals to 32, we have access to 0, 32, 64, then 96, and then 112 in the first iteration. Next 96 in the first iteration, and then 133, 65, and 97. And we also notice that in every inner loop, every access is actually a single block, and we only access to 4 blocks in one iteration. And if we are using the four-way set associative cache, then this 4 blocks should exactly fit into the 4 blocks inside one set, and we should not evict any block. And after we go back to address 1 in the next iteration, we will find the cache block still inside the cache and should have a cache hit. And if we use the same process previously to find the miss rate, we will find that the miss rate for a stride equals to 32 situation on a four-way set associative cache is 1/4. However, the question still tells us the miss rate is 1. So our four-way set associative cache is not true. We need to further divide. We need to further divide this cache into two-way set associative cache with 8 different sets. Only in that case, our 4 blocks in every iteration will not fit inside one set, and we have to evict some old blocks from the cache. And after that, we will have a cache miss for access to 1, 33, 65, and 97, and have a miss rate of 1. Okay, finally, let's use our assumption of a two-way set associative cache to test our test the case when stride equals to 64. In this case, we access 0, 64, and then 1, 65, and then 2, 66, 3, 67, 4, 68, 5, 69, blah, blah, blah. Okay, so in this case, in every iteration, we have access to only 2 blocks, which exactly fits inside our two-way set associative cache. And we don't have any cache eviction. And therefore, in the next loop, when we come back to 1, we will find the cache block for 0 and 1 still inside the cache, and we will have a cache hit for both 1 and 65. And similarly for 2, we will still have a cache hit because it's in the same set as 0 and 1, and similarly for 66. And for 3 and 67, we also have cache hits. And then when we come to 4, it's a different block than the previous 2, so we must have a cache miss here. And similarly for 68, but for the next 4 accesses, for the next 3 accesses, we should all have hits. So as you can see, in this case, in every block, we'll have 1 miss come with 3 cache hits. So the miss rate should be 1/4 or 0.25, which is fortunately consistent with our question this time. So finally, we can make a conclusion that is our two-way set associative cache assumption should be correct. And therefore, our blocks per set is just 2, and the number of sets should be 8.